It's my distinct pleasure to welcome you to the third annual Michio Yanai Distinguished Lecture. So I've attended all three, and the interesting thing that happens is that each year it's clear that the lecture has outgrown its previous venue. The attendance is just increasing, so I don't know where you will be next year, but there's Schoenberg Hall with a capacity of 500, and there's, of course, Royce Hall with 1,800. We'll see when it gets to be that big. I'm Joe Rudnick. I'm the Dean of the Division of Physical Sciences, and because of my age, I'm the Senior Dean of the College of Letters and Science. And I'd like to thank you, all of you, for joining us on campus this evening. I get to boast a little bit about UCLA. That's the privilege they grant me before I turn the evening over to the people who actually are the reason you're here. And I'm going to say something that I've been saying over and over and over again. You know, UCLA is by any measure a great institution, and it's especially a great public institution. And if you look at all the rankings that come out, UCLA comes in number 2, you know, among all public institutions in this country. You could probably guess what number 1 is. You know, it's our bigger sister, our older sister up north. Actually, we're bigger than they are, but they're older than we are. There is actually an exception to this. There's one of the most respected ranking organizations, the Higher Education Supplement of the London Times, ranks both institutions and programs. And physical sciences at UCLA ranks number 9th in the world, but number 1 among public institutions. So take that, Berkeley. And of course, our number 1 rated department, Atmospheric and Oceanic Sciences, is one of the principal reasons that we enjoy this exalted status. The members of the department are among the absolute leaders in describing and applying the science underlying the phenomena at all altitudes in our atmosphere and at all depths in our ocean, as well as the interactions between the atmosphere and bodies of water. The work being done here advances our understanding of the fundamental processes that control the environment and in which we all live, and that inform the policies that must be followed if we are to anticipate and mitigate the effects of climate change. So speaking of all this, I am thrilled that Dr. Benjamin Santer can be here with us today to share his knowledge with everybody in the audience. Tonight's lecture honors the memory of Michio Yanai, an expert in tropical meteorology and a professor at UCLA for 40 years, from 1970 to 2010. I'm honored to welcome Michio's wife, Yoko, and his sons, Satoshi and Takashi, who have joined us here today. Where are you, please? Could you stand up? And I would like to extend my personal thanks to the Yanai family for their generosity in making this lecture possible. It's now my pleasure to introduce Michio's former graduate student, Wen Tang, who will share a brief update with us on a special project to honor Michio's distinguished career. Wen?
So, as many of you know, that shortly after the Yanai Symposium a few years back turned out to be a memorial for Michio, we started a monograph, American Meteorological Society monograph in honor of Michio. And we brought together about 60 scientists in the field to work on this monograph. And it took several years. There were some unforeseeable challenges throughout, but then everybody believed in this volume, and then they stay with us. So it's now completed, and then it's being posted online, 1 article each time. And there will be a print version of it as well. And then Michio's son, Takashi, here is designing the cover. We'll bring the good news when the online posting is completed and then when the print run is completed to everyone. Thank you.
Good afternoon. I'm Jochen Stütz. I'm the chair of the Department of Atmospheric and Oceanic Sciences, and I would like to welcome you all to the 2016 Yanai lecture. And I also want to extend my special welcome to Mrs. Yanai and Takashi and Satoshi. Thank you for supporting this event. This is probably the nicest venue we had, so maybe we can stay here for a year or two, and then we'll move on. I would like to welcome all our alumni who have joined us here, and it's always nice to see you and hear some stories from our history. And also, I would like to welcome the faculty and numerous graduate students and postdocs who have joined us here today. I would also like to extend a special welcome and a thanks to Dean Rudnick. And he's been one of our biggest supporters, and I think part of the reason why we actually ranked #1. And he's been Dean for 10 years now, and he hasn't mentioned more? 10. Okay, I got that right, thanks. But it's a roundup. But he's retiring in 6 weeks, and he didn't mention that. And I think we really owe him a lot of thanks. He's supported the department. Since I've been chair, he has allowed us to grow back to our old strengths. We hired 4 new faculty members in the last year alone. I think 2 of them are here. I can see Marcelo Chemecki, who is the currently most recent hire for another 6 weeks. Then we have Rong Fu joining us, and I see Gang Chen here too. I haven't seen Jacob Bortnick, but the department has reached its strength, the largest number of faculty that we've had, I think, since about 10 years. And we're not stopping, thanks to Dean Rudnick, and we have 1 more faculty member hopefully coming in a few weeks, and we're also hiring 2 more faculty members. There's ongoing searches. So none of this would have been possible without the support over the past 10 years. So I think we all owe Dean Rudnick a big thank you. And we make sure if we end up in Royce Hall that you'll be invited. Now I'm very happy to introduce tonight's distinguished speaker, Dr. Benjamin Santer, and he's an atmospheric scientist at Lawrence Livermore National Laboratory. It's a hard name, that's why we all call it LLNL. And his research focuses on the identification of human-induced climate change in observations and also in the evaluation of climate models. And when I talked to him yesterday, he actually told me how he got into this field, and I thought that's very interesting, not just because it happened in Germany, but because it happened at a place that you wouldn't expect it. It's a German company that I personally only know for building airplanes. But in the 1980s, they already were looking at climate change, and he told me that's what really dragged him, what got him into this area. And I think, and I have to think I'm paraphrasing now, the study you worked on was the societal impact of of climate change. Is that about right?
Socio-economic impact.
Social-economic impact. So this was the early 1980s, and if you open a newspaper nowadays, you'll see that people still are discussing the same topic. So this is something that has stayed with us for quite a while. And so after he got introduced to this topic, he moved on to the University of East Anglia in Norwich in the UK to do his PhD, and then went back to Germany to work at the Max Planck Institute in Hamburg, which at this time was one of the most active climate research centers in the world. It still is, I guess. But and then in 1992 went to Lawrence Livermore and has been a scientist ever since. He's well known for being one of the convening lead authors of one of the chapters of the early IPCC, that's the Intergovernmental Panel of Climate Change reports. I think it's number 2. And he has also won numerous awards, the Norbert Gerbier International Award He's a MacArthur Fellow. He won the Lawrence Award and the DOE Distinguished Scientist Award. And tonight he will tell us how one can identify signals by fingerprints in climate change observations and models, and how you can use this to identify the human impact on our climate. So please join me and give a warm welcome to Ben.
Good evening, ladies and gentlemen, and thank you very much for kindly inviting me here. It's a real honor to give this lecture, and I'm sorry that I did not get to meet Professor Yanai personally. I'm going to tell you a little bit about fingerprinting the climate system. So how do we as scientists study the nature and causes of climate change? This isn't just a pretty picture up here. It shows you the amount of water vapor in the atmosphere on the day Hurricane Katrina made landfall. This blob here in the water vapor field is Katrina. And what this picture illustrates, I think, is that since the late 1970s and 80s, we have the capacity from space to monitor truly global scale changes in climate, to move from the local to the global. And that's been transformational, I would argue, in terms of being able to try and understand the causes of climate change. We'll get back to water vapor later in the talk. That's one of the things we try and do fingerprinting with. But first of all, let me declare my values. I always try and do that before these presentations, to tell you that I'm not just a climate scientist, but I'm also a climber. And since the age of 18, I've spent a lot of my life in beautiful, fragile, high alpine environments around the world, in the Alps, in the Himalayas, in the Rockies, most recently in Alaska, in the Juneau ice field. And the sobering thing is, forget about the fingerprinting. I've been able to witness changes over one human lifetime in these places. Some of the glaciers I stood on in the Alps when I was a young man in my early 20s are fundamentally different now. So it's in my opinion, not only a scientific issue trying to understand the nature and causes of climate change, but there's also some moral and ethical imperative to preserve these and many other beautiful places for future generations. They're in our trust. We don't own them. These are pictures here right at the end from the Juneau ice field in Alaska. And when you stand here where I took this picture and you look on the immensity of the Taku Glacier, climate change is not some theoretical academic issue. You see the signs of it everywhere. Alaskan glaciers are retreating. The only few glaciers that are not are wasting, are shrinking, even as they're melting. Meltwater from the surface is being channeled to the base. They're surging even as they're shrinking away. So go and see these things now. They won't always be there with us. As Jochen mentioned, in 1994, I received a phone call out of the blue, and a friend of mine said, Ben, you're going to receive a telephone call from the Intergovernmental Panel on Climate Change, and they will offer you the opportunity to act as convening lead author for one chapter of their second assessment report. Again, the Intergovernmental Panel on Climate Change has the job of advising the nations of the world what we know about the physical climate system, nature and causes of climate change, likely impacts of climate change, mitigation and adaptation strategies. And they're going to offer you the chance to act as convening lead author of one chapter, the chapter dealing with detection of climate change and attribution of causes. And I remember very vividly what he said to me, this will be a real feather in your cap. You should do it. It turned out that it was an experience best described as character building, I think, in retrospect. But I agreed to serve, and after 1.5 years of work and review, this was the bottom line finding of our chapter, a sentence that's forever engraved in my memory. the balance of evidence suggests a discernible human influence on global climate. So we were not saying, eureka, there's water in the bathtub, we understand everything. It was a cautious, I believe, responsible statement reflecting the then available science. But even that cautious statement caused me a lot of grief. I spent roughly 1.5 years of my scientific career defending that finding and the process by which it had been reached. And it's kind of sobering to think that until I die, I will forever be inextricably linked to that one sentence. It's sort of, we're twins. It will follow me around wherever I go. Well, the most recent assessment report of the Intergovernmental Panel on Climate Change, the 2013 report, came to a much stronger and more definitive finding regarding the reality of human effects on climate. Look at the cautious balance of evidence. That statement back then, 20 years ago, did not try and say how large the human imprint on climate was. But this most recent statement in 2013 moved far beyond temperature. It said that human influence had been detected in the atmosphere, in the ocean, in the water cycle, in snow and ice, in sea level, and even in some climate extremes. And then it used this specific likelihood language. It is extremely likely, where that meant greater than 95% probability that the statement was correct, that human influence has been the dominant cause of warming in the 20th century. So how did we get there in 20 years from the cautious balance of evidence statement to that human influence is pervasive in the climate system? Humans are no longer innocent bystanders in the climate system. Active participants is what we are now. How did we get there? What was the trajectory? That's what I'm going to try and tell you a little bit about tonight. I think it's important first to note that those findings are not a house of cards resting on one or two pieces of evidence. Those discernible human influence findings rest on physical understanding. For over a century, we've known a lot about the heat-trapping properties of greenhouse gases. They rest on circumstantial evidence, so we know that in response to human-caused burning of fossil fuels and increases in greenhouse gases, we should see certain things: warming of the oceans, increase in rise in sea level, changes in the hydrological cycle, and we see those things. So there's this qualitative agreement. Studies of the past, which many of you do here, are tremendously useful in understanding what we've observed over the last century and a half and putting that in the context of the last 800,000 years of climate history, which is probably what we can get from ice core information at the moment. And then finally, there's this fingerprint evidence, rigorous statistical comparisons of climate model simulations of the changes we should see in response, say, to human factors with hard observations. And I'm going to talk tonight about the fingerprint evidence. And first of all, I'm going to try and tell you a little bit about what fingerprinting is. Then I've used this lecture as an opportunity to review. You look in direction B, where the signal is large relative to the noise. So this was determine how we should search for some human-caused signal lurking there in the background noise of natural climate variability. What did they do? What were their contributions? Then I'm going to give you two examples. One is looking at temperature changes in Earth's atmosphere, and the other is coming back to water vapor, so that figure that we saw in the first slide, and the amount of water vapor in the atmosphere. And then finally, some conclusions. Well, what is fingerprinting? The basic premise is that different factors that influence the climate, the sun, volcanoes, human-caused changes in greenhouse gases, each one of those things has an unambiguous fingerprint. And if we move beyond global averages of temperature or moisture and look at complex patterns of climate change, you have more discriminatory power. It becomes easier to separate those different influences. again, the assumption is that each one of these things, the sun, volcanoes, human influence, have different patterns of climate response. And basically, people use signal processing methods that should be familiar to electrical engineers who do this routinely. They search for signals embedded in noisy data. And the recognition in the late 1970s was, wow, we can use those ideas, borrow from them, apply them to the climate problem, and look at the agreement between some model, computer model predicted guess of the climate changes we should see in response to human influence. And we're going to compare that model simulation with actual observations, with surface temperature data, or satellite measurements of water vapor, and we're going to use some statistic to quantify the level of agreement between the guess, the model prediction, and the actual observations. And then we're going to do the same thing and look at the sort of statistical agreement we might get between the search for fingerprint and natural climate variability. And we're going to see whether this agreement here is statistically unusual. That's the basics of it. And the nice thing is that you can test competitive hypotheses. So people routinely say, Dr. Santer, it's all the sun. I believe that all the warming we've observed is due to some uptick in the sun's energy outputs. Well, we can use this kind of fingerprint framework to test that hypothesis and see whether it's the best explanation of the available observations, as I'll show you later. Consider this. You know, again, this is getting back to something that I'm sure you read about in your newspaper even today. It's all the sun. Prominent politicians have said this. These are our best estimates. This is from the National Climatic Data Center in Asheville, North Carolina, of global and hemispheric scale changes in the Earth's temperature from 1880 through to the present. You can see warming of nearly 1 degree Celsius, 1.5 degrees Fahrenheit, over the last 130 years or so. And again, some folks have argued this is all some uptick in the sun's energy output. Okay, how can fingerprinting help us to look at that kind of claim? Well, imagine that these folks are right. Imagine that over the 20th century and early 21st century, the sun has become more active. So essentially more incoming sunlight, solar radiation at the top of the Earth's atmosphere, heating throughout the full vertical extent of the atmosphere, from the stratosphere right down to the Earth's surface. What you'd expect to see if you looked at a slice through the Earth's atmosphere from the North Pole to the South Pole, this is from a climate model simulation, in response to changes only in the sun's energy output, is warming throughout the full vertical extent of the atmosphere, from the surface right up to 20 miles. That would be the fingerprint of an increase in the sun's energy output. Now, we've known that the fingerprint of human-caused changes in greenhouse gases is fundamentally different from this. And as I'll show you, we've known this from the work of Suki Manabe and many others back in the 1960s, that the fingerprint, the vertical temperature changes associated with human-caused greenhouse gas changes are fundamentally different from the sun explains everything fingerprint. So what do the observations look like? Do they look more like the top panel, or do they look more like the bottom panel? We'll get back to that in a minute. But before we do, let's look at some of the principles, some of the principal figures involved here, and some of the history. So as I mentioned, back in the 1970s and 80s, people weren't fingerprinting. They were looking at the average temperature of the planet and trying to make inferences about causes by looking at global mean temperature. Then in the late 1970s, there was this recognition, wow, there's all this rich information in patterns, in information about seasonal aspects of climate change. And if we interrogate that information, look beyond the global mean, that one number, we have a better chance of attributing, of understanding what's going on in the climate system. So in the late 70s and 80s, then people were developing pattern recognition methods and trying to figure out which ones might be useful to us. Folks back in the late 80s were using climate models, computer models of the climate system, to try and identify what you might call canaries in the coal mine. So to look at the question, where would you look? If you wanted to find a human-caused climate change signal, would you look at temperature, moisture? Would you look in the ocean, in the atmosphere, in the tropics? Where would you look? Where would you have the best chance of finding that climate needle in the haystack? Using models, if you will, as intelligent guides to figure out how to maximize your chances of finding some human-caused climate change signal. But they weren't really doing this in observations yet. That happened really in the early 90s, where people were trying to then do this in the real world and for the first time figure out, can we see a human-caused fingerprint in observations? Then after the balance of evidence statement, there was another shift towards moving beyond temperature. One justifiable criticism, I believe, of the balance of evidence statement in 1995 was, you folks are only looking at surface temperature. If there really is some human-caused climate change signal lurking in observations, look for water vapor. Look in the depths of the oceans. Look in the hydrological cycle. Convince us. And that was reasonable criticism, and that's indeed what the climate science community did then in the late 1990s and early 21st century. More recently, folks here and a number of institutes around the world are looking at individual extreme events and trying to figure out, can we as scientists say something responsible about human contribution to changes in the likelihood of individual extreme events or some category of extreme events. Think heat waves, droughts, flooding. So that's sort of been the evolution over the last 30 plus years. And here are some of the principal figures involved. So again, another story I did not tell you, Jochen. I was at a conference in Erice in Sicily in 1980. And I played hooky when I should have been listening to a lecture on cloud physics, and, and played tennis with Professor Hasselmann, who was then the director of the Max Planck Institute for Meteorology, or one of the directors. And after our tennis game, he said, well, why don't you come to Hamburg and give a lecture when you're close to finishing your PhD? And it's funny how in all of our lives there are these moments of serendipity where one chance meeting, or in this case, one tennis match, changes your life. And I went to Hamburg, I gave a lecture, and I wound up going there to do a postdoc in 1987. And when I got there, Professor Hasselmann said, signal detection, that's a nice job for a young man. I think you should work on that. And that one tennis match changed my life, quite literally. Now, you know, Klaus was one of the figures at the forefront of this idea of borrowing from electrical engineers and figuring out how do we apply those signal processing techniques to the climate problem. And one of his key insights was this, that if you're trying to look for some human-caused climate signal embedded in noise, and this ellipse here sort of represents natural climate variability, you don't necessarily look in direction G, where the signal is very large. You look in direction B, where the signal is large relative to the noise. So this was, we need to optimize signal to noise, not the signal. And that was a key insight that was very helpful later in climate change detection and attribution work. This paper was published in 1979 and largely ignored by the scientific community for many years. And one of my jobs when I first came to Hamburg was to figure out how to apply these kind of signal detection strategies in the real world. Jerry North, professor at Texas A&M University, was also right there at the beginning of this fingerprint detection work. And one of his key insights was, this was in a paper back in 1995, that in order to improve your chances of discriminating between human causes and natural causes, you need to look at both space information and time information. For example, the sun, has an 11-year cycle roughly. And we know something about that cycle, and that enables you, if you look at the time information, to separate solar effects from other effects. So his insight was look at both. Look at the space information, look at the time information, and that'll help you. Then last year's Yanai lecturer, Suki Manabe, was not working actively on the development of fingerprint methods, but he had a key contribution to this whole field. So back in 1967, he performed some of the first simulations with a climate model where he doubled levels of atmospheric CO2. And what he found was this very curious pattern of cooling of the upper atmosphere, the stratosphere. So here you see the response of global mean temperature as you move from the Earth's surface right to the upper atmosphere. And you could see that as you ramped up CO2, you got this progressive cooling, very large cooling of the stratosphere. And you can't see it as well here, but warming of the troposphere. Now, I mention this because one knock on climate models is they're not falsifiable. They don't make predictions that we can actually falsify with data. But this was a prediction back in 1967. We didn't have the satellite data. We had sparse weather balloons measuring temperature, but they typically burst before they got up into the stratosphere. So Suki Manabe could have been wrong. And we'll see later whether this prediction that the lower atmosphere should warm and the upper atmosphere should cool, whether he was wrong or whether he was right. But it was a key insight back then. This is a friend of mine and colleague of mine, Tim Barnett at the Scripps Institution of Oceanography. Tim was also there at the beginning, a student of Klaus Hasselmann's. And Tim was looking for these canaries in the coal mine. So he was using computer models to try and figure out where would you look? You know, which variables, surface temperature or surface pressure, which variables have the highest signal to noise ratios and give you the best chance of identifying some human effect on climate. Very, very influential work back in the late 1980s. All of these guys were pioneers and in my opinion deserve medals as big as soup plates. Okay, so let's tie this together. Let's get back to Suki Manabe's prediction about how the vertical structure of temperature should change in response to increases in greenhouse gases. And let's look at how you might actually try to do simple fingerprinting. This is from some work we published about 3 years ago. And the science question, the driver here, was can we identify some human-caused pattern of atmospheric temperature change as you move from the surface right up into the stratosphere? Can you say definitively that the changes we've observed, say in satellite atmospheric temperature data, are due to human influence? So here are those satellite observations. These are beautiful measurements. These are measurements that have been made since the late 1970s from instruments known as microwave sounders, and they measure the microwave emissions of oxygen molecules. And those emissions are roughly proportional to the temperature of different layers of the atmosphere. And by measuring at different microwave frequencies, you can back out the temperature of different layers of the atmosphere. These particular satellite observations are from colleagues at Remote Sensing Systems in Santa Rosa in California. Again, you're looking at a slice through the Earth's atmosphere from the South Pole to the North Pole and from the surface right up into the stratosphere. And you see this very large warming in the lower atmosphere, the troposphere, over the Arctic, where there's been this large retreat in Arctic sea ice. And you see this cooling of the upper atmosphere with the largest cooling over Antarctica, where there's been large human-caused depletion of stratospheric ozone. So to first order, the first thing to note here is this pattern of observed change in the large-scale temperature of the atmosphere is fundamentally inconsistent with the sun explains everything. Now, the next time someone tells you it's all the sun, please ask them, why is the stratosphere cooling if all surface warming is due to the sun? the model simulations, these are from the latest, greatest model simulations performed 4 or 5 years ago. They fed into this 5th assessment report of the Intergovernmental Panel on Climate Change. And to first order, they also show this very curious pattern of cooling of the upper atmosphere and warming of the lower atmosphere. Now, there are some differences. The warming in the satellite data is larger over the Arctic than in the models, and in the tropics, it's the other way around. The warming in the models is larger than in the satellite data. Many people have tried to understand these differences and are still trying to do that. But to first order, the curious aspect of this thing is this pattern is in agreement with Suki Manabe's prediction back in 1967. This is the kind of thing we'd expect to see in response to human-caused changes in CO2. All right, so how might we look for that model-predicted pattern of human influence in the satellite observations? Well, let's imagine for a moment we look at that model Fingerprint. These are from simulations where only human factors change, greenhouse gases, particulate pollution, and we're going to look for that pattern in the satellite observations, and we're going to look at a whole sequence of satellite observations through to the present. This work was done 3 or 4 years ago, so that's why it doesn't extend right to the present. And we're going to calculate some statistic, some measure of similarity between the human influence pattern and the actual observations. And it looks like that. And you can see that this measure of similarity in the search for human influence fingerprint and the satellite observations shows a trend over time and a lot of variability. Like this dip here in 1991, 1992 is due to the cooling effect of a very large volcanic eruption, Pinatubo, which warmed the upper atmosphere and cooled the lower atmosphere, the converse of the search for human influence fingerprint. That's why there's this dip here. This big spike is the big El Nino event in 1997, 1998. So as climate scientists, we understand many of the features of this time series here, but the key question is this trend unusual? Could you get that degree of increasing similarity between the search for human influence fingerprint and pure natural variability? So if you tried to look at this in model simulations with no human-caused changes or no changes in the sun or volcanoes that give you pure internal climate variability associated with things like El Niños, La Niñas, and other modes of internal climate variability, we have many thousands of years of data from many different models, and we can calculate a similar measure of similarity that you might expect to get just by chance between the human influence fingerprint and climate noise. And the question is the trend that we saw in the previous slide significant relative to the correspondence you might expect by chance alone? And the answer is this. This shows you what Klaus Hasselmann and Jerry North and those guys were interested in, signal to noise. So how large the trend is in the similarity between the human influence fingerprint and the satellite observations relative to the chance correspondence between the human influence fingerprint and natural climate noise. And we're looking at this as a function of time. There are multiple satellite data sets here. One of the things you can see is that some of the satellite data sets now, the producers of those satellite data sets give you not one heroic best estimate, but they use clever techniques to give you a whole family of plausible observations using elegant Monte Carlo techniques to try and play through all the satellite data set construction uncertainties and give you some sense of the uncertainty in the observations. But the key thing is here that so we're looking initially over 1979 to 1988, and at the end we're looking over the full satellite record, 1979 through to 2011. Again, this study was done in 2013. The kicker is that the signal to noise ratios are huge. They're of order 9 to 11, Remember all the discussion a couple of years ago about the Higgs boson and the meaning of a 5 sigma event? Well, if these model-based estimates of internal variability are reasonable and are realistic, and we and others have looked at that and believe they are, then what this is telling you is that correspondence between the human influence fingerprint and the actual satellite observations is extremely unusual and highly unlikely to occur by chance alone. We and others have looked at these kind of things in many different ways, and that's our best understanding, that nature alone can't produce those kind of patterns of simultaneous and sustained warming of the lower atmosphere and cooling of the upper atmosphere. The best, most parsimonious explanation for those changes has to involve human-caused changes, increases in CO2 and human-caused depletion of stratospheric ozone. Okay, again, one of the knocks on this work, so this kind of work was done in the mid-90s, was you folks are only looking at temperature. Convince us. Look beyond temperature. Look at other independently monitored aspects of the climate system. So we did. Let's get back to water vapor. We did a fingerprint detection study with satellite-based estimates of water vapor. These are from something called the Special Sensing Microwave Imager, or SSMI. And what we found and claimed was that there was some emerging human-caused signal in the increasing moisture content of Earth's atmosphere, consistent with basic theory. We know that as you warm the Earth's surface and lower atmosphere, a warmer atmosphere should be able to hold more water vapor, and we found that we could see that fingerprint of human influence in satellite water vapor changes, and that fingerprint match was primarily due to human-caused increases in greenhouse gases. And again, we were criticized, quite rightly, I believe, and the criticism went like this. In this particular study in 2007, we had used a very large number of models, 20, but it was a democracy. One model, one vote. So these were models from Japan and China, the United States and Germany, France, Australia. And in that 2007 study, we argued that each one of them was equally credible. The criticism went, that's clearly not the case, Dr. Santer. They're not all equally credible. So look at this. This shows you water vapor on 2 time scales here. So down here on this axis, we see water vapor variability on year-to-year time scales, basically, on 1 to 2 year time scales. So it tells you something about how large the variability of water vapor is on 1 to 2 year time scales. And on this axis here, we see the variability of water vapor on monthly time scales. Now the crosshairs here, the X, is on these satellite observations. And what you can see is all of these flags here are models from different countries. I've skillfully disguised the actual identity of the model there using national flags. But you can see this huge range there of model performance. So there's about a factor of 6 or 7 difference in the model range of variability. And the argument went like this. Hey, why don't you just restrict your attention to the best climate models, the ones that are closest to the observations, and then repeat your entire fingerprint detection analysis? So this led to the question, how would you, in some David Letterman type sense, identify the top 10 climate models? How would you do it? Is there one statistical measure of model performance to rule them all? In a Lord of the Rings type sense, one number that you could use to identify unambiguously the best climate models? How would you do that in a responsible way? So we looked at that in a paper several years later. And we looked at these 22 climate models, and we looked at 20 different measures of how well they captured observed water vapor and ocean surface temperature. We looked at how well they did with the seasonal cycle of water vapor and ocean surface temperature, how well they did with the average water vapor and temperature in different regions, and we ranked them then, 1 to 22. And there are various ways of doing that ranking. You can either rank them based on their ranks for these individual 20 measures. That's called non-parametrically, or you can rank them based on the individual statistics after you normalize the statistics. That's the parametric ranking here. I won't get into the details, but the kicker is you want to be in this gray box. If you're in the gray box, you're in the top 10. You're the top 10 models as measured by these 20 different statistical measures of model performance. And then we did the same thing with 50 metrics, but these were tougher. We looked not at average climate, but we looked at variability on different time scales, monthly, yearly, decadal time scales, water vapor, temperature in different regions, in El Nino regions, in the Pacific decadal oscillation region. This is more challenging, tougher tests to get right. But what I want you to do here is I want you to follow the top 4 models in terms of these simpler measures of how well the models did with mean climate in the seasonal cycle. So they're the top 4 models, and it happens to be a US model, a Japanese model, a British, and a German model. And I want you to see where they wound up, the same models, in terms of these tougher tests of how well they got observed patterns of variability. None of them are in the top 10, consistently in the top 10. So the message from this was there is no one measure of model performance to rule them all. Model errors are very complicated in space and in time, so we have to look at many different attributes of climate model performance in order to identify the best and the worst models. So then we took this information and we said, okay, we're going to use these 70 different measures of model performance, and we're going to recalculate the human influence fingerprint in the water vapor field based on the top 10 models, looking at these 20 mean climate measures, based on these 50 models, based on the variability measures, and based on all 70 measures of model performance. And we could select the top 10, the bottom 10, and we could do that again non-parametrically or parametrically. That's what the NP and the PA mean. The main message here is, regardless of whether we looked at the best or the worst, these human influence fingerprints are very similar. Why? And the idea there is that this is basic physics, something called the Clausius-Clapeyron relationship, which governs the relationship between temperature changes and moisture changes. And you can see that regardless of whether we selected the best or the worst, how we selected them, in all of them, model water vapor increased virtually everywhere, with the largest increases as expected by basic theory over the warmest areas of the oceans. So the human fingerprint looked like that. It was not particularly sensitive to model quality. Now, from these simulations with no human influence, these so-called control runs, you could do the same thing and identify the sensitivity of natural climate variability in water vapor to different selections. Again, selecting top 10 and bottom 10 models based on these 20 mean state metrics, 50 variability metrics, and everything in the kitchen sink. Now, these patterns are very different from the search for human influence fingerprint. These look like classical El Nino patterns with this horseshoe-shaped structure here, and the kicker is that you see both increases and decreases in water vapor. This is getting back to what Tim Barnett said back in 1987. Young scientist, go and look in areas where the search for human influence fingerprint is spatially very different from the dominant patterns of internal variability. And that's why it didn't matter. It didn't matter how we selected the top 10 or bottom 10 models. These numbers here correspond to the 12 different cases in the previous slide. Again, these are the mean state results. These are the variability results. These are the everything in the kitchen sink, all 70 diagnostics. And what you see here is that regardless of how we selected the top 10 or bottom 10 models, non-parametrically, parametrically, which statistical measures we used to select top 10 or bottom 10 models, every one is above this significance threshold. So the significance, the signal to noise ratio is larger than we would expect by chance alone. So we addressed the criticism. We tried to see whether accounting for differences in model quality fundamentally changed our results. It didn't. And again, to me, that's the challenge in this kind of fingerprint detection work, to understand whether some claim that you've identified a human effect on climate is robust to current uncertainties in the satellite observations, in the models, in the statistical methods you use to compare simulations and observations. And you know, I'm proud of the fact that we actually addressed criticisms by doing the science, by doing the research necessary to determine whether the criticism had merit or not. Just some conclusions here at the end. I've shown you two examples here. I've shown you the vertical structure of atmospheric temperature, and I've shown you water vapor. But climate scientists have looked at many different things. Land and ocean surface temperature, temperature in the atmosphere, temperature in the uppermost 700 meters of the ocean, the height of the tropopause, the sort of boundary between the lower atmosphere and the stratosphere. They've looked at mean sea level pressure, something called geopotential height, zonal mean rainfall, humidity at the surface, water vapor, which I've showed you, continental runoff from major river basins, Arctic sea ice extent. And in all of those studies, again, people have looked at complex patterns of change, and the bottom line message is that natural causes alone in all of these things can't explain the changes we've actually observed. So from a scientific point of view, there's something beautiful about this. There's some internal and physical consistency to this story. It's not a house of cards resting solely on one observational data set or one fingerprint study. And many scientists around the world, using different statistical methods, different simulations, different observations, have helped to tell this story. So finally, at the end, the best part of the scientific journey is both the discovery and the people you meet along the way. And these are folks I've learned from, worked with, collaborated with over the last nearly 30 years trying to do this work. And that's the real reward. As I mentioned, and as Jochen mentioned, sometimes some aspects of this work are unpleasant. Powerful people don't like the findings that you reach. But that's the noise. The signal is this. You know, the signal is getting to work with friends and colleagues and establish those lifelong friendships and learning relationships. Thank you very much again for the opportunity to give this lecture.
We have time for a few questions, Joe.
So you compared models with a historical record. How do we extrapolate?
Yeah. Well, thank you very much for that question. Very relevant here because at UCLA, you have folks who try and shrink those projection uncertainties. So for temperature, for moisture changes, for sea level changes, there's a range of uncertainty in these model projections out to 2100. I haven't shown you those projection uncertainties, but they're large, and they've been with us for a long time. And we know that they're primarily related to uncertainties in model representation of so-called feedbacks, mostly feedback mechanisms associated with clouds, to a lesser extent water vapor, snow, and sea ice. So people like Alex Hall and David Nealon and others here have been searching for clever ways to relate things we can observe in today's world, present-day climate observables, to those projection uncertainties, and to say, wow, there must be possibly clever transfer functions that help us to look at how these feedback mechanisms involving clouds, snow, sea ice, and water vapor operate on short, well-observed, monthly to interannual timescales, and maybe we can learn from study of how these feedback mechanisms operate on those shorter timescales, something about which models might be more credible in terms of their long-term projections. That's beautiful work, very influential work, and I would say it's had huge impact here on the entire field, because now, instead of doing what I showed you, these broad brush statistical measures of model performance, people are looking at those kind of measures of how well models represent feedback behavior to try and identify more credible and less credible climate models. So the long-winded answer to your question is, I do think that there may be hope of reducing some of those projection uncertainties in the future. It's a tough, tough problem, but there's plenty of interesting and important work to be done on that problem, and you are leaders there.
So in the first model of the sun is increasing intensity and that's causing the change there. Why do you expect it to kind of uniformly increase the temperature of the atmosphere, not closer to the Earth for the absorbing sun one?
Yeah, I actually truncate in the lower troposphere, so I didn't include the surface, but you're absolutely right. If you extended those fingerprints down to the surface, what you tend to see is that an increase in the sun's energy output would manifest or would operate by the same feedback mechanisms, so ice, albedo feedback mechanisms. You would see some larger warming, and do see larger warming in the Arctic than in the tropics. So that's sort of missing here because this is only satellite data that I showed you. And the results that I showed you were done with one particular climate model. That solar fingerprint was with the so-called parallel climate model and was done many years ago. It would be nice to revisit that work with more recent climate models and extend it down to the surface. But yeah, there are good reasons to expect to see some latitudinal variation at the surface in the solar fingerprint.
I'll ask the last question. So
Sure.
how many fingerprints have you looked at and have you found one that doesn't show you impact?
Well, we started off with surface temperature. We moved to the vertical structure of atmospheric temperature. We looked at water vapor. We looked at ocean heat content. We looked at a number of different things. And the big puzzle was the first one. The big puzzle was atmospheric temperature. As I explained yesterday, for many years, one group involved in making these satellite temperature retrievals claimed that the lower atmosphere was cooling. And they were very forceful in making that claim. They made it again and again. And they were the only group doing those retrievals. There were no other groups that threw their hat into the ring and tried to reproduce those findings. So that was a huge puzzler. How could that be? The surface temperature data suggested that the Earth's surface was warming, and yet the satellite data was apparently showing that the lower atmosphere, the troposphere, was cooling, and that was in fundamental contradiction to basic theory of how the atmosphere should respond to CO2 increases. Fundamental contradiction to the surface temperature measurements. But the narrative was satellite data are more reliable, and this is the killer evidence that falsifies everything. That was a big problem, but then science is all about reproducibility. And other satellite retrieval groups tried to independently reproduce the results of the first group, and they couldn't. They found out that the first group, the one that had claimed that the troposphere was cooling, had forgot that the altitude of satellite decays over the lifetime of the satellite, and that affects the swath of the Earth's atmosphere that the satellite sees from space. Another thing that they got wrong was that some of these satellites drift by hours over their lifetime, and that affects the time of day at which they see the Earth's daily temperature cycle. You have to correct for that orbit drift in sampling the daily temperature cycle. And in doing that drift correction, they made a sign error. They literally got the sign wrong. So as heretical and paradoxical it sounds, that was an area where there was some huge mismatch between basic theory, the expected fingerprint of human influence, and the observations. But in the end, the models and basic physical expectation and looking at other variables like water vapor were able to point us in the right direction and show that the simulations weren't fundamentally wrong, but this one group's satellite retrievals was fundamentally wrong.
If you don't mind. Go ahead. First of all, thank you very much. That was really excellent. I really enjoyed it. How would you recommend, suggest, help, advise dealing with confirmation bias when you're talking with folks that just don't want to hear anything?
Well, I'm funded by the U.S. Department of Energy. They fund virtually all of the research that I do. And I firmly believe that if you receive government funding, you have to be accountable. You have a responsibility to go out in the public arena and answer questions that people have. Even folks who are skeptical about you and everything you do, everything I presented here today. I learned bitterly back in 1995, 1996, that just doing the science and just publishing the papers was not going to cut it. And that I had some larger responsibility to be accountable, to answer questions that people had about my research. And I've tried hard to do that in the last 20 years, and I'll continue to do that. Because as we see very vividly, particularly in the last year, there's a continuing need to bring people back to the science and explain to them, this is what we know, this is how we know it, this is what's uncertain, and we need to continue to do that.
Okay, please join me thanking Ben again for this inspiring talk. And this concludes our presentation. I would like to thank you all for coming, especially our alumni and friends who join us once a year at this point, and we're always happy to see you. I'd like to thank you all for your support, and especially the Yanai family for making this event happen. And maybe if you have some other questions, Ben is going to be around for a little while. So thank you all.